The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
All right, so our first speaker, Michael Sprinkel, is an Associate Director of Materials at the Virginia Center for Transportation Innovation and Research. He's been with the Virginia Department of Transportation for over 40 years, doing research in areas of polymers, concrete materials, repair of bridges, sealants, and other types of applications, pavements as well. He is here to talk to us today about corrosion reinforcement in high-performance concrete applications. So, welcome, Michael.
Thank you, Michael. And it's certainly my pleasure to be here this morning to honor Richard Weyers. I first met Richard in, I think it was around 1988, and he had been awarded the Sharp 1 project on protection, repair, and rehabilitation of concrete structures, which was a 4 to 5 year project. And he hired me to work on rapid repair techniques, and I'll have to say my involvement with Richard in that project probably was one of the biggest factors in my career as far as providing me with the many opportunities to travel around the country, meet with other DOTs, look at overlays in other states, and put together a report with Richard on time and within the budget. So ever since then, I've been working closely with Richard Weyers on various projects. And so today, I think it's fitting to talk about corrosion of reinforcement in today's high-performance concrete. Controlling corrosion of the reinforcement continues to be the most controversial challenge for professionals responsible for reinforced concrete structures exposed to chlorides. For most of my career, folks have been debating how to deal with controlling corrosion and reinforcement. Decades ago, quality concrete had lower strengths, higher permeabilities, but fewer and tighter cracks than the concrete used today, which is often called high-performance concrete. And I can go to bridges right in Charlottesville, Virginia, go under the decks. Back in the early days, we weren't using stay-in-place forms. I can go under some of these decks, built in the 60s. There's not a crack in the concrete deck, still today. High-performance concrete we use today typically has high strength, very low permeability, but unfortunately a lot of wide cracks. Now, one can argue, in fact, when I wrote the paper around which this presentation was prepared, one of the reviewers said, well, if it's got cracks, it's not high-performance concrete. And so one can argue that concrete with wide cracks is not high-performance concrete. And that mixtures with high strength, low permeability, and tighter cracks, which would really be high-performance concrete, can be used in many situations. Over the past 20 years, DOTs have reduced cracking in high-performance concrete by using less cement, shrinkage-reducing admixtures, and using lightweight aggregate for internal curing. However, cracking continues to be one of the most significant problems facing the concrete industry. One of the reviewers of my paper said this was not so, that we don't have a problem with cracking in our concrete structures. Well, if we don't, then ACI is making a mistake, big mistake, because the control of cracking induced by volume changes in plastic and hardened concrete has been identified as an industry-critical technology by the Strategic Development Council of the American Concrete Institute. and they've awarded a $1 million project over 5 years, which was initiated in January a year ago, January 13. And the title of it's Reducing Volume Change-Induced Cracking in Concrete, Field Implementation and Evaluation of Crack Reduction Technologies. Significant problem. Low permeability. We've been able to get very low permeabilities in our high-performance concretes since the beginning of these concretes in the 90s. And it's typically achieved, this low permeability is achieved by replacing a portion of the Portland cement with fly ash and or slag, sometimes silica fume, but most often fly ash or slag. And in Virginia, typical additions are 25% type F ash and 50% slag. Unfortunately, because the fly ash and slag contribute very little to early strength, 25 to 50% of the Portland cement is often not removed. And the total cement material content of these high-performance concretes is higher than in the past, often more than 700 pounds per cubic yard. The additional cement used to achieve the higher early strength to facilitate accelerated construction causes an increase in curing temperatures, drying shrinkage, and wider cracks. Now, if you're using this high-performance concrete in pre-stressed or post-tension structures, these structures will probably last 100 years because you keep the cracks from forming by pre-stressing or post-tension in the concrete. So today with high-performance concrete, there's no question in my mind we're going to have many structures that's going to last more than 100 years. However, with conventionally reinforced concrete structures, particularly bridge decks, which are flexural members, we're going to have a shorter life than many of the structures of the past because of the wide cracks in the concrete that are typically caused by shrinkage and temperature differentials. This is a picture of the underside of a bridge deck on US 123 over the Occoquan River, constructed in 2007. This is about 20 miles south of D.C. And you can see the transverse cracks, spaced 3, 4, 5, 6 feet apart. It varies depending upon the design of the deck. But this is very typical of the underside of decks in Virginia and in many other states constructed over the last 20 years. And you can see they're leaking. They're full depth transverse cracks caused by shrinkage of the concrete because of too much cement. Another picture, full depth transverse cracks on the underside of a bridge on I-81 near Marion. Again, you can see the calcium hydroxide stains. Salt and water goes through these cracks every time it rains, every time snow falls on the deck. The pictures you've seen are typical of decks constructed in Virginia over the past 20 years. Now, these cracks typically align with the reinforcement in the transverse direction as parallel to the cracks, and they intersect the reinforcement that's in the longitudinal direction of the crack of the deck. But these cracks are typically wider than 0.2 millimeters. Most of the time they're 0.5 millimeters. We've measured many of them, but 0.5 millimeters. Any crack that's as wide as 0.2 millimeters or wider is going to leak and allow chlorides into the crack. The cracks allow chloride and moisture direct access to the reinforcement in the deck. Today, the liquid sodium chloride applied provides a more corrosive environment than the granular material, the granular chloride and abrasives we used to use decades ago. We put down liquid today because it's so much more effective in preventing the formation of ice and snow. But at the same time, it's so much more effective in corroding the reinforcement and deteriorating the concrete. Full depth leaking transverse cracks in decks, in my opinion, provide a very corrosive environment. You have, in a bridge deck in Virginia, repeated cycles of wetting and drying and liquid chloride applications on the deck, particularly providing an environment that, in my opinion, is similar to the splash zone in a saltwater environment. And this picture from William Hart just shows the critical corrosion environment they have in Florida. But if you think about a crack in a bridge deck, it's just as similar, wetting and drying, salting after salting, as well as flexural movements because of the tractor trailers driving over the bridge. Also, we have some very aggressive lab tests that in many cases really don't give you an accurate prediction of service life because they're so harsh. But I believe in the situation of cracks in decks, many of these very aggressive tests do provide an accurate prediction. In these full depth leak and transverse cracks, the concrete quickly has a low pH and it's subjected to wetting and drying cycles. The rebar surface corrodes rapidly. There's no protection provided by the concrete in the vicinity of the crack. Water washes the corrosion deposits away, allowing the steel surface to rapidly corrode, and the cycle continues until the steel section fails because it's too weak to handle the shear, tensile, and compressive stresses. What we have here in these cracks is anode corrosion. The rebar section that intersects the crack provides a small anode that's driven by a very large cathode in the rest of the deck, where the high-performance concrete has high quality. So the steel section necks down rapidly in the wet-dry, chloride-contaminated, low pH environment. In this situation, A615 steel rebar would have a very short service life. Now, how does epoxy perform in a situation like this? Epoxy-coated rebar continues to be the most used corrosion protection system by most DOTs. Research that we did in Virginia indicated that, and Richard Weyers was the leader in all of the research we did on epoxy-coated rebar, but that research shows that the coating provides corrosion protection initially, depending upon the condition of the coating and the quality of the coating. But over time, the coating deteriorates and delaminates, allowing water and chlorides direct access to the steel surface. This coating can actually trap moisture, preventing the water from evaporating and allowing the rate of corrosion to increase. This is a picture of corroded epoxy-coated rebar. Now, this is not in a crack. This is a longitudinal construction joint, typical of the construction joints we have in many decks in Virginia today. And the reason for this is we originally built the bridges on the interstate system around 1970. And then those that received a protective overlay in the 80s, that deck is still there today, 1968, 1970 concrete. But the decks that did not get protection applied by an overlay installed in the 80s had to be replaced in the 90s, and this was one of those. And the typical way to do deck replacement now is not to close the bridge, but to close half the bridge. Replace one half of the deck, put traffic on the new concrete, and then replace the other half. And so you end up with one or two longitudinal construction joints because of the way we replace these decks. And this is just one of those. This deck failed in shear in the left wheel path of the travel lane after only 17 years in service. And you can see the picture there of the leaking construction joint. In the picture, the green coating has turned brown due to exposure to moisture and chlorides, wetting and drying cycles. The crack, in this case, the construction joint's about 0.5 millimeters wide, which is typical of the full depth cracks we get high-performance concrete in our decks now, which are leaking. The resistance to flow of your chlorides and moisture through a crack would actually be greater than this construction joint, which is pretty much a straight shot. So there, you should be getting even worse corrosion where you have your full depth cracks. And this is a picture of Richard after this deck had this shear failure of the deck. Fortunately, no one was injured. It was actually reported as a pothole. But Richard went down to the site south of Blacksburg there, and we found 3 decks where the deck, these decks had been reconstructed about the same time in 1992 using the same techniques And all three had a closure pour connecting the two halves. It was 3 feet wide. And the 3 decks, and all 3 decks, this closure pour was ready to completely fall through due to corrosion of the reinforcement in the construction joint. Richard found there was actually no steel inside the coating in some locations, a phenomenon only reported by Florida back in the 90s. So here it was in Virginia in leaking construction joints. We were so fortunate there wasn't a major accident because of the situation that was there. And I'm saddened by the fact that FHWA requires us to inspect these bridges every 2 years, and that there wasn't at least one inspector looking at one of these 3 bridges that didn't report all this rust stains in that crack many years before we had a failure. It should have been, you know, found out and measures taken to prevent the failure, but it didn't happen. VDOT's low-cost solution to this problem is corrosion-resistant reinforcement in wide cracks. And corrosion-resistant reinforcement can last more than 100 years. And high-performance concrete can last more than 100 years. So why not mate it with reinforcement that can last more than 100 years? It just makes good sense. So even when the concrete cracks and the steel is exposed to wetting and drying and de-icing chemicals, if you're using stainless steel or other alloyed steels that will give you a very long service life, then you can get bridge decks that's going to last close to 100 years. VDOT discontinued the use of epoxy-coated rebar in 2010 after this problem with the bridge deck on I-81. And the bridge engineer, we'd recommended changing to stainless or other corrosion-resistant reinforcement. Richard had recommended that for years. And we finally decided we were going to quit making this recommendation. And then after the bridge engineer in Virginia drove down and saw this hole in this bridge on I-81, he immediately went back to the office and wrote the memorandum indicating we're going to corrosion-resistant reinforcement. It took a failure to get VDOT to make this change. And it's amazing in our life that we don't change anything until we have a failure. Fortunately, this time there was no accident or injury. What are some other strategies that folks use today? Cathodic prevention, something you have to maintain. You have to have a competent electrical staff to maintain the cathodic protection systems. Polymer membranes can bridge over these cracks, but you got to deal with replacing the asphalt surface periodically, replacing the membrane. You can route and seal the cracks. You can inject them with epoxy. Now, solid stainless. We've been using solid stainless since 2010 now. Increases the installed cost of rebar by $1.24 per pound on average in Virginia. It's installed cost compared to epoxy, which increases the deck cost $74 per square yard. This is 2011, 2012 bid tabulations. Alternative treatments really cost quite much more. Concrete overlays, $150 a square yard. So hydraulic semi-concrete overlays. Membranes and asphalt, $110 per square yard. You got to redo the asphalt part of the overlay every 10 to 15 years. Or you can route and seal every 5 years, or you can inject the cracks that cost about $80 a linear foot. All of these methods are far more expensive than just building the deck with corrosion-resistant rebar. Okay. This is a picture of an attempt to repair cracks on I-81. And there they've used put epoxy down and put a carbon fiber mesh in it. This was epoxy injection. This was route and seal. This is typical of the decks on the interstates in Virginia built in the last 20 years. Corrosion-resistant rebar versus more expensive methods. We've had no issues with the supply of stainless steel or other corrosion-resistant rebar. VDOT uses solid stainless for bridges on interstates and heavily traveled primary routes. It uses A1035 for rural and urban volume roads. Recent efforts to reduce cracking include use of lightweight aggregates, shrinkage-reducing admixtures, type K cement, less cement. All of these have shown promise in reducing the cracking index. So in conclusion, corrosion-resistant rebar is a cost-effective solution for our problem with corrosion reinforcement and full-depth cracks. Decks can be constructed with high-performance concrete that has fewer cracks by using lightweight, coarse aggregate, or tighter cracks, fewer and tighter, shrinkage-reducing admixtures, type K cement, and less cement. So we recommend at this time continue to use corrosion-resistant reinforcement and try to develop mixtures that will be less prone to cracking. And these are the references that should be available to you if you want to download the presentation later. Thank you.